let's look at this problem. This problem has two parts. The first part is to replace the applied external force and moment by a single force system, equivalent single force system. And we need to determine the magnitude of the force, specify its location, and we need to illustrate it on a separate sketch. And then we need to determine the support reactions at the fixed support point A. For this problem, you do need to consider the thickness of the beam. So the dimension is given. That's a hint that you need to consider the thickness of the beam. So let's first look at the first part to basically add all of these applied force and moments together. So right now, we don't consider equilibrium. We're just adding them together. We will have resultant force along the x direction that equals to, we will have this 30 kilonewton force with x component pointing to the left direction. So again, according to convention, this is a positive to the right. So we have a negative 30 kilonewton sine 30 degree. And then we have this 26 kilonewton force. The direction is given by a right triangle, 5, 12, 13 right triangle. And the x component is going to be a 5/13 component, and then it's pointing to the positive x direction, so plus 26 times the component 5/13. So when you do the calculation, this will give you a negative 5 in the unit of kilonewton. And then resultant force along the y direction, load only. Again, right now we're not considering equilibrium. We're not setting it to 0. It's not 0 anyway. So we have a negative 30 kilonewton times cosine 30 degree, negative because it points down. And then for the 26 kilonewton force, the vertical component is a 12/13 component, also pointing down, so minus 26 times 12/13, and this equals to a negative 50 kilonewton. Now, before we replace the entire system by a single force system, we will replace it by a one force, one moment system placed at point A. So we will do that. Resultant moment about point A. We're just basically summarizing all the moments about point A. Okay, so we will have counterclockwise by convention, that is positive. We have a free 45 kilonewton meter couple moments, and that is clockwise, so that is a negative 45, taking that. And then for the two forces, the forces have x and y components, and both x and y components have moment about point A. Okay, so let's look at this vertical component first. This vertical component has a magnitude of 30 times cosine 30 degree. The negative sign is because it's having clockwise rotational effect about point A. Okay, its moment arm is 2 meter. And then let's look at this horizontal component, this component right here. This component right here is actually having counterclockwise rotational effect about point A with a moment arm of 0.3 meter. Okay, because of this thickness that we cannot ignore. So we will have a plus 30 times sine 30 degree. That's the magnitude of the force multiplied by the moment arm of 0.3 meter. And then let's move on to the 26 kilonewton force. This vertical component is causing clockwise rotational effect with a moment arm of 2 plus 1 plus 3, 6 meter. So we will have the magnitude 26 times 12/13, that's the magnitude of the force, multiplied by the moment arm of 6 meter. And then if you look at this horizontal force, it is also causing clockwise rotational effect about point A with a moment arm of 0.3 meter. So minus 26 times 5/13 gives you the magnitude of the force times the moment arm of 0.3. And that's everything. And as a result, that is a negative 239 kilonewton meter moment about point A. So first we will replace our load system by a single force and a single moment about point A. So we're going to put it right here at point A. All right, so right here at point A. So that will be 5 kilonewton X component to the left and a 50 kilonewton Y component vertically down. So together, this force looks like this right here with a magnitude of square root of 5 squared plus 50 squared, and that equals to 50.2 kilonewton. And also there's a moment right here, and that moment is going to be actually clockwise because it's negative 239 kilonewton times meter. But we're going to move this force a little bit away from point A. So this is point A right here. We're going to move it a little bit away from point A so that the vertical component of this resultant force will be able to create that 239 kilonewton meter moment. Therefore, this force placed at this location alone has not only the equivalent force, but also it creates the same moment about point A. What happens is its own vertical component creates exactly 239 kilonewton meter moment about point A. Therefore, this distance, x bar, equals to 239 kilonewton meter divided by the vertical component of this resultant force, which is your 50 kilonewton. This is in absolute value, and that will give you a distance of 4.79 meter. Okay, so this is your, if you only look at the red force, this red force represents the final answer for the first part. That's your single force system placed at the location right here. That is at a 4.79 meter away from point A. Okay, so now with that said, we're going to move on to the next part, which is to determine the support reaction. So we have already determined the equivalent system. So we're going to use the equivalent system, 50.2 kilonewton here, which is equivalent to a 5 kilonewton here and a vertically down 50 kilonewton here. And that's it. That's the entire load. That's why we do the replacement. But don't forget at point A you have a fixed support. If it's a fixed support, you will have all three support reactions. We will have your AX right here, AY right here, passing through point A, and your support moment MA. You have these three unknowns. So now, because of equilibrium, we can start to write our equilibrium equations. Resultant force along the x direction equals to our unknown support AX minus 5 kilonewton, and that equals to 0. Resultant force along the y direction equals to AY, so this is vertical up is positive, minus 50 kilonewton equals to 0. And lastly, resultant moment about point A, counterclockwise, is positive. The reason why we choose point A to summarize our moments is because the two forces, AX and AY, unknown forces, pass through point A. Therefore, they do not create any moment about point A. So we will only have an unknown MA. This is the couple moment unknown. Okay, and then minus your 50 multiplied by 4.79 moment arm. You can do that, or if you remember, oh, that is 239 from the previous step anyway, kilonewton meter, and that equals to 0. So from there, you can easily solve for the three unknowns. Your AX is simply 5 kilonewton. Your AY is 50 kilonewton. and your moment unknown is solved to be 239 kilonewton meter. This is counterclockwise, it's positive. So you can see how these results look just like the results from the previous steps. However, the previous step, these are applied loads. And then what you have solved in this step are the support reactions. The support reactions, as you can see, are equal and opposite to the applied loads. It's because they are there to balance these loads in order to keep the structure in equilibrium.